Next we have the sixth exercise. You recall example 12.1.6 where we came across this metric space. At that time we declared that this is the metric space. Here the set is the set of all n tuples of real numbers, and we have the Euclidean metric here, whose definition we already know, the one involving that square root of sum of squares, that thing. So we have to now prove that it really is a metric and it makes this pair a metric space. Let's solve this. So we start the solution by taking two such n tuples and let them be x and y with these coordinates. X has the coordinates xi and y has the coordinates yi, which of course are real numbers. Now let us recall what dl2 is. The dl2 distance between x and y is this. Note that it's the square root, so we have included this exponent 1 over 2, and it's the square root of this sum of squares of corresponding differences of the coordinates of these two n tuples. Alright, so now if x and y are equal, then what will happen? Then obviously by the definition of equality of two n tuples, each xi would be equal to yi, and as such each term in this sum would be equal to 0, whose square root is also 0. So in this case, if x and y are equal, then the dl2 distance between them is 0. And this is the first axiom in the definition of a metric, first condition. Or you can actually directly also write that dl2 x comma x is equal to 0. For the next axiom, we consider x and y to be distinct. If that's the case, then at least one xj should be different from the corresponding yj. So in this sum, there would be one term corresponding to that index j. That difference would be a non-zero real number. Because xj minus yj would be a non-zero real number, so its square would be a positive real number. Note that xj minus yj may be negative, but it's not 0. It is either positive or negative, and as such its square would be a positive real number. Then what would be the effect of the positivity of that square on this sum? That would make this sum itself a positive real number. Why? Because the other terms, all the terms being squares, are non-negative real numbers. So the least all of these terms can be is 0. None of them can be negative. So whatever positive you are having from the term xj minus yj whole square, that cannot be reduced by the other terms because of their non-negativity, and that is why the sum would stay positive, and so its square root would also be a positive real number, which is this dl2 distance between x and y. So we have verified the first two conditions for a metric for this function dl2. Now next we have symmetry. So let's see what happens. Symmetry is pretty obvious because xi minus yi whole square is equal to yi minus xi whole square. Because there is a square, it does not matter whether you write xi minus yi or yi minus xi. For all I, it's clear that this sum, if you have xi minus yi, is equal to the corresponding sum where you have yi minus xi. So their square roots are also equal, and that is why the dl2 value of x comma y is equal to the dl2 value of y comma x. And as such, dl2 satisfies the symmetry condition. And finally, we go for triangle inequality, for which we are going to need another n tuple besides x and y. So let's see that next. So accordingly, we take this n tuple set whose components are coordinates rz I in Rn. Then by the previous exercise, The previous exercise had some inequalities, Cauchy-Schwarz inequality. Actually, it starts by proving an identity, you remember, which we proved by induction. And then using that identity, we derived the Cauchy-Schwarz inequality. And then using Cauchy-Schwarz inequality in turn, we finally derived another inequality which we can call the triangle inequality. That we are going to use here. So what do? We start with this dl2 value of x comma z. So by definition, this is equal to this. You may notice that I haven't written the index and I am not writing the variation of the index I. I varies from 1 to n. It is there, but I am not showing it. Sometimes to avoid writing what is obvious, we do write like this, although it's not advisable. Actually, if you have to write a lot of these things, you can sometimes, out of laziness or what, I don't know, you can write like this. But you should be careful to not follow this practice when more than one index are involved. If two indices are involved, here we have only I, but say you have double summation and you have I and j. There if you do this, then you will quickly get confused. But anyway, you understand what this symbol means. So this is our dl2 value of x comma z. Now next what we do in the next line, in place of xi minus zi, we write xi minus yi plus yi minus zi. So that these two cancel out and we get this back. Square, do not forget that we have a square over this. And there is of course a square root over the entire sum. And then in the next step we use that triangle inequality from the previous exercise. Let us recall what that inequality was. Its structure was like this: summation ai plus bi whole square, but not simply summation, square root of summation ai plus bi whole square plus, okay, not minus, that is less than or equal to square root of summation ai square plus square root of summation bi square. That ai now is xi minus yi, and in place of bi we have yi minus zi. So that is why we have this. You can see that here, square root of summation ai plus bi whole square is less than or equal to square root of summation ai square plus square root of summation bi square. And if you look carefully, this is the dl2 value of x comma y, and this is the dl2 value of y comma z. So we are almost there. We just have to write one more line. So let's do that. Okay, so this expression is equal to dl2 of x comma y, which is this, plus dl2 of y comma z, which is this. So that way dl2 of x comma z is less than or equal to this plus this, which is our triangle inequality for a metric. And that is why dl2 is a legitimate metric on Rn, and this is a metric space. Okay, so let's see the next one. Next we have the seventh one, and this time we recall this metric space. Metric space means we have to prove that it's a metric space, and this is the taxi cab metric d little l1, and we encountered this in example 7. So let's show that this is a metric. The solution is almost identical to the previous one. Again we start by taking two n-tuples x and y in Rn, but this time the metric, the distance function is different. It is this. Now we do not have square and square roots. We have a simple sum, but we should be careful with the terms. It's not just xi minus yi, It's the absolute value of xi minus yi. And here also you can note that I haven't written I equal to 1 to n. But I suggest that you write it. Okay. I have to write a lot here in this tight space. That is why I am discarding those simple things which are easily understood. So then what do? We go for the axioms one by one. If x is equal to y, same as before, each xi is equal to yi. And that is why you can see that all the terms of this sum would then be equal to 0. And so the sum would be 0, and that's why the dl1 value of x comma y would be 0. In this case, if x is equal to y. Next, if x is not equal to y, then some xj is different from the corresponding yj. But then again, the corresponding term here would be positive. And whatever I said about this similar situation in the previous solution, here also the same thing will happen. Here also, all the terms are non-negative, and if one term is positive, then the others cannot change that positivity, because the least they can be is 0. None of them can be negative to affect the positivity of that term, mod xj minus yj. So the entire sum remains positive, and that's why this is positive. And again, for the third axiom, symmetry, this time also, just like squares, the absolute value also remains unchanged if you change the sign of the number whose absolute value you were considering. So mod xi minus yi is equal to mod yi minus xi for all I. And that is why the dl1 value of x comma y and y comma x are equal. So that means we just have to now prove triangle inequality. So let us next go for that. So for the triangle inequality, we again take another n tuple z like before, and then we start with the dl1 value of x comma z. By definition, that is this sum. That means summation of the terms of this form, absolute value of xi minus zi, where I varies from 1 to n, which we are not writing. Now we can write this xi minus zi like this. Here also it's matching with the previous solution. Xi minus yi plus yi minus zi. Then this is less than or equal to this, where the absolute value got distributed over these two terms of the sum. And this is where we have used our ordinary triangle inequality that we have in the system of real numbers. But there is something more that needs to be said about this step. Forget about this summation for a moment. Say you only have this single expression, absolute value of xi minus yi plus yi minus zi. By the triangle inequality, ordinary triangle inequality, this is less than or equal to just this sum. Forget about the summation. Mod xi minus yi plus mod yi minus zi. And this is true for all I. So that means you are getting n inequalities. You add them up. If you do so, that will give you this inequality. Okay, so that's the there is an intermediate step, means an explanation. And now next what you do, you can write this sum as the sum of these two sums, which actually follows from the fact that addition of real numbers is commutative and associative. That's why this happens. Or you can refer to one of the properties of finite series from the 7th chapter, I think, in volume 1. So there one of the properties tells us that we can write that, or we can write this sum like that. Can split it into two sums. And this one of course is dl1 of x comma y, and this one is dl1 of y comma z. So that way we have the fourth axiom also verified for dl1, and as such dl1 is a metric on Rn, and Rn with respect to this metric becomes a metric space. Let us see another one, the next one. Next we have exercise 8, and in this one we have to prove the two inequalities in 12.1, and those two inequalities are these, this one and this one. So they are saying that for any two n tuples x and y from Rn, the dl2 distance between x and y is less than or equal to the dl1 distance between x and y, which in turn is less than or equal to the square root of n times the dl2 distance between x and y. So these inequalities relate the dl2 and dl1 metric. So let's now prove them. We start the solution like this, because here we have already mentioned that x and y are coming from Rn. So let us just write their components. Let the components of x be xi and the components of y be yi. Alright, so actually the first inequality we are going to prove is the first one, namely that this dl2 is less than or equal to dl1. So we start with dl2, and instead of simply taking dl2 we take its square, so that now there is no square root involved. But the term, the expression inside the square root of course is there, summation xi minus yi whole square, where I varies from 1 to n. You note that here again I have written I. This time I am showing the index and its variation, because now it is important. So now next what we do, we add an extra term to this one in the next step, and that extra term is this. Let us first understand what this is. It's actually a double summation, in fact, or you can also treat it as a single sum, but with two indices I and j, which are, you can say they are independent of each other. Each one varies from 1 to n. So I is also varying from 1 to n and j is also varying from 1 to n, but there is a condition, and that's the only way they are kind of dependent, that they are never equal. Okay, in what sense are they not equal? If they are both varying from 1 to n, then there will be instances when they are equal. In this sense, that means if you are varying I and j simultaneously, you will get these terms. Oh, and one more thing, let us see what the terms are. Absolute value of xi minus yi times absolute value of xj minus yj. From all those terms in this large sum, we are not considering those terms where I is equal to j. That's what it means. Because of the non-negative nature of these absolute values, the entire sum is non-negative, greater than or equal to 0. So if in the least case where all of these terms are 0, then this is equal to this. Otherwise, if you have some positive term in this sum, then this is greater than this. So in general, this is greater than or equal to this. And you may notice one more small change. In place of ordinary square, we are writing square of absolute value, which we can write because x square is equal to mod x square. This we already know about real numbers. Now, what is this going to give us? Let's see. Now, before we go to this part, let me make one small correction. There will be a 2 here. Okay, I did not write 2 previously, but we need 2. But that does not, of course, change anything that I said just now, that this will be greater than or equal to this. Now, in place of this entire thing, we write summation of mod xk minus yk, because I and j are involved here. So without giving preference to any one of them, I am just simply using another name for the index now. As k varies from 1 to n, but it's square. The question is, how is this thing equal to this? Do you recall this identity from your school algebra? We of course first first of all encounter, the moment algebra starts, very quickly we encounter the identity that a plus b whole square equals a square plus b square plus 2ab. But then after some time we also encountered this identity that a plus b plus c whole square equals a square plus b square plus c square plus 2 times ab plus bc plus ca. And this identity is true in general, where you may have any finitely many terms in the sum. So what goes on when you expand such a square is that you write the sum of the squares of the individual terms, which is what you have here. And in place of a, b and c, this time we have absolute value of xi minus yi. Here we have 3 terms, here we have n terms. I should say this one. Okay. So this part of the expression corresponds to this plus 2 times the sum of the cross terms, taking 2 at a time. For example, a, b, b, c and c, a. Note that cross terms I am saying because we are not again considering a and a, because those terms, those type of things have already appeared here. And these appear twice because once it appears, if a and b are involved, once you have ab and then with that you also have ba. If you write this as a plus b plus c times a plus b plus c and you do the multiplication, you will understand why these things come. So this part of the expression corresponds to this. In order to have distinct terms multiplied, we need this I not equal to j. So that's how we have this corresponding to this, and that's how this is equal to square. But what is the thing inside square? This is just the dl1 value of x comma y. You see, it does not really, of course, matter whether you write k here or I here. These are just dummy variables. So this is dl1 of x comma y whole square. So now you are almost there. Square of dl2 is less than or equal to square of dl1. So now you just have to take square root, but wait, not so fast. You can take square root and simply write dl2 less than or equal to dl1 because they are non-negative real numbers. That is why. So let's do that. So that will give us the first inequality. Then we will go for the second one, which is slightly more complicated. We are going to need the Cauchy-Schwarz inequality to prove the second inequality. So let us first recall the Cauchy-Schwarz inequality and let us try to remember this, okay, carefully, because I cannot afford to just keep it like this as I am doing calculation. I need this space as well. So let us first recall that Cauchy-Schwarz inequality is about a list of numbers ai and bi, where there are n ais and n bis, and because this is a list, repetition is possible. So then the absolute value of summation of ai bi, okay, let's remember this, okay, or you can just simply open the text and see the Cauchy-Schwarz inequality. You keep that in front of you. Summation ai bi as I varies from 1 to n, its absolute value is less than or equal to the square root of summation of ai square times square root of the summation of bj square. Alright. Now what do we do? We, of course, this time we have to prove, let's also recall the inequality that we are going to prove now. dl1 of x comma y should be less than or equal to the square root of n times dl2 of x comma y. So we start with dl1 of x comma y and we start with its square. Alright, so we write what it is. dl1 of x comma y is summation x u. You can understand at this stage that something complicated is going to happen. So we are freely using very weird names for these indices, summation indices, in order to just keep them distinct from one another. So here say it is u. Okay, summation u varying from 1 to n, absolute value of xu minus yu, square of that. Square of that means what? That means multiplying two copies of the same thing. But because in this multiplication actually summations are involved, so we are going to use different indices. Say this one has index I and this one has index k, but note carefully that actually this and this are the same thing, which is this sum. Because here also you have mod xi minus yi and here you have mod xk minus yk. Now we are going to do the multiplication, but of course we are not going to write everything down. We are going to do it slightly cleverly. Again, before we get rid of this part, let's recall summation of some terms which are products of two terms. Absolute value of that is less than or equal to sum square root square root times square root of again sum square. Alright, so let's now go for the next step. So we multiply these two sums like this. We are treating the second sum as a single real number, which it is. Okay, so you just think of this as something, say b. Okay, and then you are multiplying all the terms of the first sum by b. So that way b comes with all the terms of the first sum. Alright, so that means this single sum, which is a real number, is now with all these terms, mod xi minus yi times that. So this is with mod x1 minus y1, mod x2 minus y2, all the way up to mod xn minus yn. Now, is there any negative number involved anywhere in this? No, because we have absolute values everywhere. So in place of this sum, we can actually also imagine absolute value. And this is where you can use Cauchy-Schwarz inequality. Do you see the left hand side of Cauchy-Schwarz inequality here? I mean, after imagining that we have absolute value also. What was the left hand side? Mod summation ai bi. Okay. So we have that here. What is our ai? We have summation and mod is there outside. We are imagining because everything is non-negative. ai is mod xi minus yi. In fact, let me write. Okay, so say this is our ai. And what is our bi? What is our bi? Each bi is equal to this sum. See, in the beginning itself I said that in the list of all these a's and b's we may have repetition. In this case all the bi's are equal to this. So these are all my bi's. So according to the Cauchy-Schwarz inequality, what shall we then get? Then this absolute value of summation ai bi is less than or equal to this. Square root of summation ai square, so the ai's are this, so we have square. This part is less complicated. Times square root of summation bj square, and in fact that's why I have written j equal to 1 to n. But each bj is this, so it's square. That's why you see square over the entire sum. Now the application of Cauchy-Schwarz inequality is clear. Now what are we going to get from this? That's what now matters. Let's see. Next, note carefully that this entire square root is nothing but the dl2 distance between x and y by definition. But what is happening to this part? Here we are looking at the square root of a sum where all the terms are same, and that too each term is a square. So first of all you can take that square outside the sum, and then you can take its square root, so that way you are going to get this without the square. Note one more thing, that we are cancelling square and square root because whatever ultimately we are left with, that is a non-negative real number, so there is no problem in doing that. But that leaves us with this, because now after almost everything has gone outside of this sum is left with each term equal to 1, each term being 1. So what is this sum? This sum is just n, so that means here we are looking at the square root of n, and this thing is nothing but the dl1 distance between x and y. And recall that we started with the square of dl1 x comma y, so that way that dl1 x comma y square is less than or equal to this. So now we are almost there. You just have to cancel dl1 x comma y from both sides, but be careful, this can be 0 also. In that case you cannot cancel. So let's write the last part. So after doing that cancellation, we get our second inequality, provided that the thing we are cancelling is the positive real number. Remember that you are not cancelling a common term from both sides of an equation. It's inequality, so positivity is required. But what happens if it is not positive? Then it is equal to 0. But because we have already proved that dl1 is a metric, so this can happen only when x is equal to y. But why? That is because if x is not equal to y, then by the second condition of a metric, d of x comma y, dl1 of x comma y has to be positive. So that means in this case x cannot be different from y, x has to be equal to y. But in that case dl2 of x comma y is equal to 0 by the first condition applied to the metric dl2, and that way in this case also you don't actually need this. In this case you straight away simply have this inequality where both sides are 0, so actually you have equality. So that way we have proved the second inequality as well. And let me just stop here itself. There are other exercises as well, so that we will prove next week. So see you next week with more exercises and their solutions. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.